traditional and emerging parasite in Tunisian marine ecosystem, with a particular focus on their distribution, bioaccumulation, and potential ecological implications. Every year, millions of tons of plastic debris enter marine ecosystems. Over time, like wave action and microbial activity, fragment this debris to microplastics, particles smaller than 5 millimeters, and nanoplastics below 100 nanometers. These small particles are persistent, mobile, and bioavailable, and their large surface area allows them to interact with UV radiation, salinity, also organic matter, and microorganisms. Through these processes, they undergo surface cleaning and carry chemical additives that were originally entered in the plastic matrix. Among these additives, plasticizers and particularly phthalate esters, also known with the acronym PAE, are of major environmental concern. Unlike pigments or fillers, plasticizers are not chemically bound to the polymer chains, and this means they can leach out easily into the surrounding water, sediments, and biota, effectively transforming plastics into chemical vectors. So once released, these compounds can move through the food web chain from plankton to fish and ultimately to humans. Plasticizers such as ethyl phthalate, also known as DEHP, D-butyl phthalate, DBP, and the isobutyl phthalate, DIBP, are widely used to make plastic flexible and durable, especially PVC. However, over the last decade, these compounds have been recognized as endocrine disruptors and toxic contaminants with adverse effects on reproduction, growth, and metabolism in aquatic organisms. As a consequence, the industry has developed so-called non-phthalate plasticizers, also known with the acronym of NPPs, such as diethylexyl adipate, DEHA, and diethylexyl terephthalate, DEHT, as supposed safe alternatives. Yet, these substitutes share similar psychochemical properties, such as high lipophilicity and low water solubility, meaning they can also persist, bioaccumulate, and potentially cause comparable ecological impact. Despite their increasing use, environmental data on NPPs remains scarce, particularly in marine ecosystems, which motivated our investigation. So here we summarize the main differences between PAE and non-phthalate plasticizers and PPs. Structurally, PAE contains abenzene ring esterified with alkyl chains, whereas NPPs derive from adipates and terephthalates, lacking the aromatic core. This structural difference is often claimed to reduce toxicity, but evidence suggests otherwise, cioè both groups are hydrophobic and fully biodegradable. Understanding the comparative behavior in the environment is therefore crucial to assess whether replacing PAE with NPPs truly reduce the ecological risk. And this is precisely the central question of our study. So the overreaching aim of this study was to evaluate the presence, the distribution, and ecological risk of traditional and alternative plasticizers in a representative Mediterranean marine environment. Specifically, we sought to quantify 10 phthalate esters and 8 non-phthalate plasticizers in both seawater and fish. To assess spatial variability comparing area under different degrees of urbanization, industrial and touristic pressure, to investigate seasonal trends distribution peaks to human activities and environmental conditions, and to determine bioaccumulation patterns in Spirus aurata, a key commercial and ecological species, and also to estimate ecological risk using the RQ approach, uh, also known as risk quotient. Altogether, these objectives allowed us to characterize not only contamination levels, but also the environmental dynamics and potential risks associated with emerging plastic items. So the study was carried out along the Messina coastline, located on the central eastern coast of Tunisia, facing the southern Mediterranean Sea. And this area represents a strategic ecological and economic zone characterized by a mosaic of anthropogenic activities, including aquaculture, tourism, urban discharge, and fishing, all of which can contribute to plastic and chemical pollution. We selected five sample sites distributed along approximately 40 kilometers of coastline, each characterized by different levels of human pressure. So, Site 1 in Mahilia near the main urban center local harbor, Regisce, a semi-urban site with moderate domestic inputs, Salacta, influenced by seasonal tourism, Kebba, exposed to industrial effluents in aquaculture, and Menulek, a comparatively pristine reference site. Um, the region is influenced by the Mediterranean climate with not dry summers and mild wet winters, and by hydrodynamic variability driven by winds and coastal currents that may favor the dissipation of microplastics and their associated chemicals. Altogether, this setting was useful to investigate how human activities and seasonal changes affect the distribution and bioaccumulation of pesticides in a coastal marine ecosystem. So, sampling was conducted monthly over a full annual cycle to capture both spatial and seasonal variability. The surface water samples, almost 500 ml each, were collected by scuba divers at a depth of 8 meters using 15 bottles to avoid contamination. For the biological components, adult Spirus aurata were collected monthly from aquaculture cages located near two reference sites, Mahilia and Kebba. The fish averaged around 24 centimeters in length and 330 grams in weight, and all handling was performed under sterile contamination-free conditions. So, muscle tissue were dissected, wrapped in aluminum foil, and stored at minus 20 Celsius degree until analysis. In total, 330 samples were processed, 3 replicate samples. Sampling were mostly performed at each site, 165 for water, and the same for fish, providing a robust data set for statistical and risk analysis. So, importantly, all materials used were glass or metal, and no plastic equipment was allowed, eliminating the risk of background contamination. So, this section, a quantification following a modified version of the protocol, water samples were pre-concentrated using the C18 solid phase extraction cartridge, rinsed and eluted with a bill assay, and the extracts were then evaporated to dryness and reconstituted with exime. The internal standards were added for PAE and for NTP to ensure accurate quantification, and the analysis was carried out by gas chromatography, GCMS, operating in selective ion monitoring mode for maximum sensitivity and selectivity. So this approach allowed us to detect even the trace level of compound with high reliability and precision. So before interpreting any results, analytical validation was crucial. So linearity was excellent with S-squared values above 0.98 for analytes. And the limits of detection ranged between 0.03 and 0.3 microgram liter, and limits of quantification between 0.1 and 1.2 micrograms liter. The recovery rates were consistently high between 93% and 102%, and the precision values below 8.2%, both intra and interday. These figures confirm the robustness of our analytical procedure and the reliability of the concentration data. The statistical analysis included descriptive statistics. One way ANOVA, we took a postdoc to evaluate spatial and seasonal differences, the person correlation among congenies, and the ecological risk classification based on L2 values, from low risk to moderate risk and high risk, when L2 values was greater than 1. Let's now move to the result. Beginning with the contamination patterns observed in seawater, out of 18 target compounds, 8 were consistently detected, 6 PAE and 2 NPP, confirming their pervasive presence. The sum of PAE concentration were with a mean of 0.17 mg. The NPPs represented only by the DEHT detected with a mean of 0.6 mg. Among individual compounds, DEP, DDT, DIDT, and DEHP were the most abundant PAE, while DEHP dominated the NPP group. These values indicate continuous and widespread contamination throughout the year, reflecting both land-based and marine sources. Notably, DEHP, that supposed several alternatives, reach levels comparable or even higher than DEHP, demonstrating its increasing environmental prevalence. The seasonal evaluation revealed clear and consistent patterns. Highest concentration of PAE were recorded during summer months between Jan and September, coinciding with higher temperature and tourism-related activities. DHT and DEHA showed increasing concentration from spring to winter, peaking between September and January. Lower levels were observed in autumn and winter, when both industrial activity and solar radiation are reduced. So these results suggest that different emission sources and psychochemical behaviors drive the seasonal variability of PAE and NPPs, indicating that both environmental factors and human activities strongly influence contamination dynamics. The common known gift-head sibling is, and scientifically known as Sparus aurata, exhibited higher levels of both PAE and NPP, confirming their bioaccumulated behavior, and therefore proving to be an effective bioindicator of placental contamination. In muscle tissue measured as dry weight, the sum of PAE averaged 5.58 mg, while the sum of NPPs reached 26.3 mg, showing a significant accumulation of both groups. Among single compounds, DEHP reached 3.05 mg and DEHT up to 23.25 mg. This represents up to 100-fold enrichment compared to seawater concentration. Such accumulation likely occurs through dietary exposure, as microplastics and dissolved contaminants are ingested retained in muscle tissue. So, notably, NPPs were found at higher concentration than PAE, suggesting that their growing industrial use is already reflected in marine organisms. The seasonal bioaccumulation trend mirrored the variation observed in seawater, confirming that fish exposure closely we follow environmental availability. These findings underline that even alternative pesticides are readily bioaccumulated by marine organisms, posing potential risk to the aquatic food web and ultimately to human consumption. So when we look at the spatial distribution of pesticides along the Marsilia coastline, the patterns becomes very clear and quite telling. Concentration were not uniform across sites. They showed marked variability depending on the degree of human activity in each area. The highest level of both PAD and NTP were recorded at Keba and Selasta, and these are zones characterized by intense anthropogenic pressure. Keba hosts industrial facility and aquaculture farms, while Selasta experiences seasonal tourism and coastal development. In contrast, Retice and especially Malulek show a much lower concentration, acting almost like natural background sites with minimal human infected. The overall gradient, the S4 site 4 greater than the S3, followed by S1, 2, and 5, perfectly mirrors the spatial patterns of urbanization and coastal use. This means that the contamination we observe is not random and it is strongly driven by local pollution inputs such as wastewater discharge, port activities, aquaculture operation, and boat traffic. In other words, the chemical fingerprint of each site reflects its specific anthropogenic signature, confirming that even within a relatively short stretch of coast, human influence leaves a measurable trace in the marine environment. This spatial evidence reinforces the idea that microplastic-related contamination is a localized but persistent phenomenon closely tied to the intensity and type of human activities occurring native. To evaluate the potential ecological hazard, we applied the risk quotient IQ method, comparing measured environmental concentration with predicted no effective concentration. In seawater, DEHP exhibited higher AQ values and DEHP showed values above 1, indicating high ecological risk for aquatic organisms. DIDC showed moderate risk with RQ values between zero point 0.1 and zero point 0.2, while DEP and DDC generally present lower risk levels. Interestingly, DEHP, originally developed as a green alternative, contributed significantly to total risk, highlighting that NPPs are not necessarily safer replacements. Overall, these assessments underscore the importance of including both PAE and NPPs in environmental monitoring and risk management strategies. So let me now move to the discussion, where we try to interpret these numbers with needs in a broader environmental context. What our study clearly demonstrates is that microplastics are not just inert particles floating in water. They are active carriers of chemical contamination capable of transporting both traditional and alternative pesticides throughout the marine environment. Interestingly, we found that the so-called non-phthalate pesticides, which were introduced as a safer alternatives, are neither were nor harmless. So the contamination levels we detect along the Marsilia coastline are among the highest ever reported for Syrian method environment. And this was particularly evident for DHP and DEHP, whose concentration exceeded those found in several European and Asian studies. When we look at the patterns, we can see clear links to human activities, higher levels near aquaculture area, falls touristic zone, lower levels where anthropogenic impact is minimal. All of these evidence supports one central conclusion: the shift from phthalate to non-phthalate pesticides has not solved the problem of marine contamination, but it has simply changed its chemical form. Therefore, from our One Health perspective, these compounds that have the same level of attention, monitoring, and regulation as traditional pesticides. In conclusion, this study sheds light on an aspect of marine pollution that often goes unnoticed, the chemical dimension of microplastic contamination. What we found along the Venetian coast clearly demonstrates that even in the absence of visible plastic waste, the ocean and sea continues to bear the signature of our daily plastic use throughout the plasticized that leach into seawater and accumulate in marine organisms. The presence of both phthalate and non-phthalate plasticizers that persistent across the season and their bioaccumulation in fish together tell a simple but powerful story. Substituting one group of additives with another does not necessarily reduce environmental risk. These findings remind us that tackling plastic pollution is not just about removing debris from the sea, but it also means addressing the invisible chemical legacy that remains behind. Looking ahead, our research opens the door to broader investigation, so future work should aim to integrate chemical monitoring, ecotoxicological testing, and ecosystem level assessment so that we can better understand how these contaminants interact, move through food webs, and affect marine life over time. Ultimately, only by adopting a truly integrated and preventive approach consistently with the One Health vision, we'll be able to safeguard both marine and ecosystem and human well-being. So this closes my presentation, and thank you very much for your kind